Hello, everyone, and welcome to our live session for today, Thursday, November 7th. My name is Matthew. I am one of the course staff for our online classes, and we really appreciate you being here with us today to talk about astronomy, and we are looking forward to your questions. So for those of you who are new to our live sessions, here's the way it works. Post those questions in the in the chat. We see every question, but please ask it only once. If we don't get to your question right away, we may be getting through a backlog of questions. We also have emails that we need to take. We do try to go in the order that we get questions, but we also jump around to try and get a variety of topics and to give more people an opportunity to ask questions. We also keep these at a beginner level. So keep that in mind when you're asking questions on the chat. We don't usually pick high-level, deep mathematical questions to answer on this stream. Chris, why don't you introduce yourself, and then you usually have a topic for us to discuss to maybe guide some questions. If you want to give everybody a welcome, then we'll get started.
Yeah, welcome everyone, however you found this stream, to the live sessions. We do it every few weeks, and we've been doing it for years. And there's no particular news story I want to highlight this week. Obviously, we had a pretty important election here in the United States, which is going to affect science policy very strongly, and scientific agencies will be impacted by this, and it's not clear how that's going to shake down. Okay, the floor is open for your questions.
Excellent, thank you, Chris. The first question that we have is from Isbayaman, who asks, Sir, I would like to know, is there any way we can discover an exoplanet using machine learning, data science, with the data sets we have from the NASA Kepler archive, if we train a learning model?
Yeah, good question. The answer is yes. It's already being done. It's already been done. There are a number of papers, more than a handful even, that involve exoplanets detected through machine learning, artificial intelligence methods. And so sifting through the Kepler data, the large amount of Kepler data accumulated over 5 years, it's challenging. It's very noisy data. The signatures of exoplanet transits are quite subtle, especially when they're near the detection limit. And machine learning has definitely been used to find exoplanets that would have been difficult to find by hand or by eye. It's also been used to try and find unusual signatures of eclipses or transits that maybe weren't anticipated by scientists, and that's one of the things machine learning is good for, actually, is to going out of the box and looking for anomalies, if you like, or interesting signals.
Excellent, thank you. The next question is from Andreas, who asks, Hi, I've learned recently that there are no green stars. Is it correct that this is not specific to stars, but rather a common feature of black bodies, given the way that we perceive their net color?
Right, so the perception of color and its relation to astrophysical color is interesting, because most stars and objects that are considered black bodies, or their thermal spectra with a particular mean temperature, they have a large range of wavelengths. So while the sun may appear to be a yellowish star to our eyes, it's emitting radiation across the visible spectrum and into the UV and the infrared, just as a broad spectrum. So when we talk about green is a monochromatic color. I mean, in a rainbow or in a spectrum, green is a particular wavelength, around 5,500 angstroms. So if any star, for whatever reason, had an unduly strong amount of radiation at that wavelength, then it would look green. But of course, stars in general don't have that narrow range of wavelengths. So even if you have a star which has a peak energy at the wavelength that we would call green as a single color, it's going to on average appear to be a milder form of yellowish orange perhaps. So we never actually see green stars. The only place where we see something green in space is in the monochromatic or very narrow wavelength range of an individual spectral transition. So for example, there are oxygen lines around 5,000 angstroms, which if you made a narrowband image, just filtering out those particular range of wavelengths, you'd see nebular emissions that were green. And that's reflecting a much narrower range of wavelengths of a particular spectral transition of oxygen.
The next question is from Not a Builder. Hello, sir. In my country, we don't have any degrees in astrobiology. I'd like to know if a biochemistry or molecular biology bachelor's can apply for a master's in astrobiology.
I think so. You'd have to make up some possible deficiencies in physics and astrophysics, but definitely a life science degree, a bachelor degree, would put you in the scope of a PhD, or there are very few PhD programs. There are more master's programs. And because the people who operate advanced degrees in astrobiology understand that most people don't have an initial training across all those fields, they tend to provide a set of courses that are self-contained and give you all the background you need. So you have to look carefully at the program you're interested in and see what their required and elective courses are that they offer, just to make sure you can fill in the gaps in your knowledge.
The next question is from an email. Wendy asks, can you please explain why NASA chose to go to Europa when Ganymede has a larger ocean?
I think it's true that there are underground or subterranean water deposits and bodies in the solar system, and Ganymede is a bigger moon, has a larger subterranean ocean. I think the choice of Europa is based partly on historical reasons, because Europa was the first watery moon of Jupiter that we studied back in the 1970s with flybys. So we have more information on it, and therefore more information to design a mission around. And also it is a compelling target because in this case we can see the icy pack that almost certainly covers an ocean, and we know from magnetometer readings that there is water under that ice. So there's just much more convincing evidence as you start planning a mission that there are liquid oceans to study. And I think that's why Europa got most of the attention.
The next question is from a apparently very precocious high school student. So the infinite equation is in Bangladesh and would like to know if you have any suggestions for how to start an independent research project or to find a research question if you're in high school. And it sounds like a kind of an open question for anybody who's interested in getting involved in research in astronomy who is not already in an astronomy program. Right.
Well, I mean, the easiest way, but not for everyone, depending on where they live, is to use a local connection. So if you're in high school especially, you should be looking at your local university, college, small college, even community college, for whether you can get a research internship or relationship. Because universities actually have to make special arrangements to have minors or people under the age of 18, if you are in high school, come on campus. You know, there are safety and liability issues and security issues, et cetera, et cetera. So it isn't unfortunately trivial for high schoolers to work on university campuses, but that's the easiest way to do it because it's direct and you'd be mentored and you'd be maybe working in a lab and working with real data. If that's not available to you in the town you live or the country you live, there are some ways to do that online, but it gets more difficult. And probably the most useful general advice is if you want to get your feet wet in the kind of data that astronomers deal with and the questions they're asking of the data, you should find a citizen science project you can contribute to, because that is by no means a watered down research experience. Many of them are very well designed and addressing important questions, but they're open to everyone. They're carried out online on the internet. They don't cost anything. And so that's, I mean, you're not at the center of a small research group, so it's not the ideal research experience, but it's definitely a way to get yourself established in some kind of research.
Thank you. The next question is from Ragnar Lodbrok, who's on with us live, who asks, do all planets, stars, and galaxies rotate? Do they rotate in a predominant direction, clockwise or counterclockwise, throughout the cosmos?
So I wouldn't say that everything rotates, but rotation is a ubiquitous feature of the physical universe, because all the objects we see, the objects that are spherical essentially, which would be all planets and many moons and all stars, are in rotation because they formed from large nebulous amounts of gas that probably had a very initially small amount of rotation that got amplified by contraction, conservation of angular momentum. So we typically always see stars rotating, we always see planets rotating, and there's coherence in the way planets spin which is the same angular momentum vector as the spin of the star that they orbit. So yes, rotation is a common feature of the universe, and in galaxies rotate also, all galaxies essentially, as well as we can measure. So I would never say there are no objects that have no rotation. There are bound to be a few, but generally because of the way things formed, there are small chaotic turbulences in the gaseous distribution of the universe that lead to vortices or eddies or net amounts of angular momentum, and then that gets amplified when the objects collapse and form.
Excellent, thank you. The next question is from Sohini, who asks, can space exploration help in solving problems on Earth like climate change?
Well, NASA has always had an interest in Earth-looking satellites. So we think of NASA as sending, Apollo to the moon and contributing to the shuttle and the space station and doing distant work beyond Earth. But many of the satellites that NASA has launched have actually been Earth-observing satellites to monitor geology or biology or vegetation, and they have very important environmental monitoring capabilities, and there are more and more of these satellites. So it is an important piece of the climate change situation to have good data from satellites that can track using infrared and optical methods all manner of things that are diagnoses of the health of our environment. So NASA has been doing this for a long time and will continue to do it, we hope. With the new Trump administration, all bets are off, but I think that NASA likes to have this as part of its portfolio.
The next question is from one of our live participants. David asks, what could cause the moon to no longer be synchronously tidal locked to Earth, such that we could eventually see the far side of the moon?
I think given the orbits and the situation we're in, that's really unlikely to happen, with the caveat for a very long time. So at the moment, the moon is gradually moving away from the Earth. The Earth is gradually slowing down in its spin, and that's a transfer of both angular momentum and energy. And if you follow that process for literally several billion years, there will actually come a point when the tidal lock and grip of the moon on the Earth lessens to the point where it's no longer true that we never see the other side of the moon. And of course, in some very far distant future, if the solar system survives that long, you might actually have the moon detach from the Earth and float off into free space.
The next question is from Kevin, who's on with us live, who asks, my question relates to primordial formation of neutron stars. I'm curious to know more about their properties, specifically their density and their content of energy. So how do neutron stars form, and where do they come from, and how do they originate?
Neutron stars are collapsed stellar objects that are the densest forms of normal matter known, because the density is the same as that of an atomic nucleus. So we're talking about a star that has the entire star core collapsed a few times the mass of the sun, that has the density of an atomic nucleus. So fantastically dense compared to normal matter or the air we're breathing or anything like that. They form at the end of a massive star's life when the star ejects some of its envelope, and then with no more pressure support from fusion reactions, the core collapses in a gravitational free fall, and that compression associated with that collapse and the force of gravity essentially forces electrons and protons to merge in a sort of reverse version of beta decay and turn into neutrons. And with the neutrons having no electrical charge, they can sit right next to each other. And so there's no electrical resistance to keep the matter puffed up or at a low density. And so it goes straight to nuclear density of matter, making them the most extreme normal objects, black holes being slightly abnormal, that we know of in the universe.
And I guess the follow-up is, what gives them their various properties? The energy, is it entirely based on their mass, or are there other qualities that determine some of its properties?
So yeah, neutron stars and any stellar remnant is dictated essentially by mass. And in fact, the initial mass of the star is a predictor of its fate. So if you have a star that's 11 or 12 times the mass of the sun, then it's fairly safe to predict that its fate will be to die as a supernova, leaving behind a neutron star. If it's somewhat more massive, you could have a supernova and then a black hole. And if it's less massive, down to range of the sun's mass or a few times the sun's mass, you end up with a white dwarf. So mass is completely determining of the future fate of the stellar remnant, and roughly its mass too. But the exact mass of a neutron star is hard to predict because it depends how much mass is lost later in the star's life when it goes through unstable fusion phases.
The next question is from Rajarshi, who's on with us live. Quantum physics says that we need to observe something in order for it to be in a particular place, collapsing its wave function. But we can't directly observe distant galaxies whose light hasn't yet reached us. So how is it that this quantum mechanic effect works with our observations of galaxies?
It's not clear that you can project quantum effects, which are the realm of the very small subatomic scales, to large macroscopic objects like galaxies. So the fact that there are galaxies we can't see and may never see is a function of the rapid expansion of the universe. It doesn't have anything to do with quantum mechanics per se. And their invisibility, the fact that we can't see them but might at one point in the future, does not depend on atomic physics in any way. So it's tricky to make a direct relationship between quantum theory or the uncertainty principle or anything like that and macroscopic objects, especially galaxies.
Excellent. The next question is from Craig, who asks, I have been told that the WOW signal from 1977 has been solved. Do we know what made that WOW signal, or what's the current thinking about its origins?
I haven't seen a recent paper on that, but the WOW signal was a radio glitch, if you like, seen at Ohio State Radio Observatory. There's a football field which was laid out with dipole arrays of radio antennae, and so Ohio State was using this in the 1970s. It got decommissioned eventually, to listen for artificial radio signals, and they found this famous signal, and in the presentation of it, the radio intensity is put onto a strip chart. And so it's a waving pen, if you like, where the amplitude of the signal is shown on a strip chart. And the WOW signal was identified as a very strong, a booming radio signal that only lasted a short period of time, then went back down to zero and never repeated. And the technician or scientist on duty wrote "wow" exclamation next to the signal and consulted the rest of the team, and they wondered if it was an alien signal. I don't know that it's been solved in a sense that there's no diagnostics you can do for what happened that long ago, 50 years ago, in a lab that's been dismantled with a telescope that no longer exists. It's almost certainly it was an anomaly, possibly within the lab or possibly actually outside the lab, coming from an external source of microwaves or radio waves, which can happen from an alternator, say, or various pieces of electrical machinery that are malfunctioning.
Excellent, thank you. The next question is from one of our live participants, Deborah, and her question is, why is it that Vega does not have any exoplanets?
Well, Vega is a star that has a young debris disk, and so Vega has been observed, and actually quite recently, by the James Webb Space Telescope. That's been in the news just in the last few days. So Vega is a young star, fairly massive star, more massive than the Sun, and so its debris disk has been studied actually for decades, going back well before James Webb to the Infrared Astronomical Survey, the IRAS satellite, in the 1980s. And if you blot out the star and look at this debris disk, you might anticipate that there would be exoplanets forming in that debris disk. But somewhat surprisingly, there are no massive Jupiter-like exoplanets. Techniques are not sensitive enough to find Earth-like planets in a debris disk that are just forming. So we might just imagine that that's because it's caught early in its evolution and it takes a significant time for planets to form by accretion.
This next question, Sarab Shukla is on with us live and asks a question that is just kind of on the edge of our upper limits of what we can really address on here, but maybe we can give it a try. How does the alignment of magnetic fields within star-forming regions and Fermi bubbles show mechanisms between star formation and galactic scale magnetic fields?
Well, so the galaxy is threaded by a magnetic field, of course, a fairly weak magnetic field. And when stars form, they essentially squeeze the magnetic field lines. In the collapse, those lines are frozen, and so that's how you end up with a star with a magnetic field. So we have magnetic fields. We have a bubble. A Fermi bubble is just a high-energy evacuated region. It's called Fermi because they're typically observed or detected with the Fermi telescope at gamma ray wavelengths, or they've seen at X-ray wavelengths because the gas is very hot and diffuse. So there's very complex astrophysics in star-forming regions, and it does involve magnetic fields, which we think facilitate the collapse of stars. But those magnetic fields are also threading much larger regions of space. So you have particle acceleration, you have aurora glow, nebular glow, and all sorts of interesting phenomena in star-forming regions.
Excellent. The next question is from Ranjan, who's on with us live, who asks generally, how is, my interpretation of this, so the specific question is, how is the angle of observation and angle subtended by accretion disks around black holes determined for Event Horizon Telescope, JWST, and Chandra? How do telescopes tell how big these accretion disks are?
Well, the telescopes, if we're talking about the Event Horizon Telescope in particular, observing in millimeter radio wavelengths, they're not actually directly observing the accretion disk. With some of these black hole observations, what you're actually observing is the shadowing of the accretion disk, because you're observing hot gas that's swirling around the accretion disk. So you do have to make a model of the geometry of the situation and where the hot gas is to understand how it looks through a telescope. And you can't actually get inside the accretion disk with any of these methods, of course, because it's a boundary, it's a limitation to our knowledge.
Excellent. The next question is from Karen, who's on with us live. Maggie Adarin Pocock states that our moon is an unusual one in the solar system. If there's no moon similar to ours in the solar system, then why would our moon be so unusual?
It is unusual because it's the largest moon relative to its planet in the solar system. The moon is not the largest moon in the solar system, and the Earth is not the largest planet, but the ratio of the two is quite significant. And that's anomalous because of the way that moons form. Moons form essentially from the debris disk around a planet that forms, and that debris disk usually only has a few percent of the mass of the planet that will form. So that's the region, that's the regime in which you expect planets and moon masses to be. And our moon breaks that rule. So we either think it was captured from space within the solar system after the Earth formed, or it was formed by an impact on the Earth from a Mars-type object very soon after formation. And the evidence is shifted mostly in the direction of an impact hypothesis, and that's how we think the moon formed. And there's some evidence geologically for this from the Apollo moon rocks that were brought back. Other moons are much smaller. Just to take Mars, Mars, of course, has two very small potato-shaped moons. They're so small they're not even formed round by gravity. Mars is a quarter the size or mass of the Earth, but its moons are far smaller proportionally. So those are very small moons, and that's more typical of what we see in the solar system.
Excellent, thank you. The next question is from Terrence, who asks, when are they going to retrieve the Mars samples?
It's unclear. The Mars sample return mission is in budget trouble. Its budget is ballooned to probably over $11 billion. And Congress, who has to pay for this, the taxpayers, of course, in the end pay for it, but Congress, who gives NASA their budget, is very unhappy. And so NASA has been forced to go back to not back to the drawing board, because they're not going to redesign the entire mission, but go back to the engineers and the mission planners and retool the mission substantially to try and cheapen it, or to very strongly cap the cost so that we know there's no cost overrun beyond the budget level agreed upon. And it's not clear they can do that. It's a very difficult, multi-stage, high-risk mission, and the samples, as we know, are already being cached on the surface of Mars. So they're being stored in vials and left at places where a subsequent mission is supposed to pick them up and bring them back to Earth. So Mars sample return has sort of started in this multi-stage process. But the costs are very high, and it's not clear, but possibly the private sector, Elon Musk and Jeff Bezos with their two space companies, may be invited to jump in and find a way of doing sample return cheaper and quicker.
That actually kind of brings us close to our next question. Arif Roni asks, it seems that the SpaceX owner is actively involved with the presidential election activity. Do you think that this means that significant progress might be happening in Mars missions in the near future?
It's not clear. The reading the tea leaves for what will happen under a second Trump administration for NASA and space science is very unclear. There's a lot of hints that federal science agencies will have their budgets cut and will be forced to trim their sails. But that may not be true for NASA, because Mars sample return and going to Mars and being first to various planetary targets is a matter of national pride. And so the directive may just be to keep doing these missions because we need to keep our status as the premier space power. Remember that China is highly competitive in space, and they're heading for some milestones that the United States may not be able to achieve in the same time frame. So this is all going to heat up, I think, next year.
The next question is again from Terrence, who asks, why is the planet Uranus north and south poles tilted differently than the other planets?
We don't know, because it's very hard to get the archaeology of the solar system. We see the solar system as it is. We can infer the past history based on current properties, but it's an unreliable process, because the solar system is a complex, chaotic system viewed over billions of years. The best guess, however, is that it was an interaction with a Kuiper belt object or an outer solar system object that tilted Uranus on its side, essentially, giving it a 87-degree tilt relative to the ecliptic. We can't prove that, though, because the interaction happened probably billions of years ago, and the interloper has long since gone. So it will, for the while, remain just a hypothesis.
Excellent, thank you. For those of you who are still on with us, if you could hit that like button and subscribe to the channel. Is just a quick reminder to do that. We'll remind you again at the end. That helps us get the word out about future live sessions, and it will send you announcements when we have future live sessions. The next question is from Pathy, who asks, new information from the James Webb telescope has helped us to learn more about space and beyond. How will it help us to understand or solve our origin?
James Webb is probably not going to solve the origin of the Earth or the origin of life on Earth or anything that's that essential to humanity. It's a deep space telescope, so it's really almost all of its targets are involved looking out in space. Of course, how it may indirectly talk about our origins is by cinching down or deflating some of the precepts of the Big Bang model of the origin of the universe, including us. And also exoplanets, the life on exoplanets, to show whether life on Earth was a unique accident or has happened elsewhere. And it is likely that James Webb will make inroads on that question in the next decade.
Excellent. The next question is from Terrence, who would like to know if we are going to get hit by the sun's corona or a photon storm from the sun's corona next summer.
We're in this high period of solar activity, and the predicting of how the solar cycle goes from within the solar cycle is very difficult. Solar cycles are not highly predictable. The fact that there is a cycle is understood and predictable. That period doesn't change. But the intensity of the sunspot minima and maxima are very different from cycle to cycle. So I think actually there's no good prediction of what is going to be going on next summer, except that we're still on the trailing edge of a period of solar increased activity. It's just not clear how much.
The next question is from one of our live viewers who would like to know, let's see, Rajarshi would like to know, do you think that we are well on our way to becoming a multiplanetary species? But do you think that we could ever be multi-galactic, or is that just too far?
Multiplanetary species, yes, probably, but not for decades. That's a stretch goal, given that we've not sent humans back to the moon in over half a century, and it's proving expensive and difficult to see the path towards a moon and a Mars base, although I do think they will happen. And these are just the nearest two objects, the moon and Mars. Venus is near also, but not a good place to go. Intergalactic travel is completely beyond the pale. It's science fiction, because there's no propulsion method known that even it could get us out of the solar system in timescales of less than centuries or millennia. And even, of course, at light speeds, it will take you hundreds of thousands or millions of years to travel between galaxies. So I think intergalactic travel is essentially not a real thing for any species living in the universe as we understand it. The scales are just too vast.
The next question is from one of our live participants. When are they going to have satellites that can see the chemical makeup on planets' atmospheres? I'm assuming they mean exoplanet atmospheres. When will we be able to observe exoplanet atmosphere chemical makeups?
It's coming. We already have some simple observations of exoplanet atmospheres. They were done in transit spectroscopy by the Hubble Space Telescope. Hubble has done that for 5 or 6 planets. And Hubble is still operating and may do a handful more, but Hubble is constrained by its fairly small mirror size. James Webb is going to do more of this. It'll be working in the near infrared, but that's okay because there are plenty of spectral features to look for in the infrared. And that is a major part of the James Webb Space Telescope agenda, is to pick the best, most likely nearby exoplanets where you can get good data with a large telescope and do this very difficult experiment of blacking out the much stronger light from the star, spreading the reflected planet light into a spectrum and looking for biomarkers or signatures of life. That experiment is coming. Simple versions of that experiment have already shown that atmospheres of hot Jupiters or massive planets, not Earth-like, include carbon dioxide, water vapor, and a few other sodium, a few other elements. But nobody's seen oxygen yet. That's one of the key biomarkers.
So the next question is from Arif Roni, who has a question about your thoughts on Sabine Hassen Felder's existential physics topics such as nature of time, beginning of the universe, structure of matter, constraints about what we can do and limits of what we can know. I mean, obviously you can't touch on any of all of those topics, but do you have any thoughts on any of those ideas that you think are particularly interesting? So I can go over those again if I'd like to.
I mean, I'll give a short answer because that's a big question. I mean, I'm familiar with Sabine Hassen Felder's work. She's a very respected physicist. She's a great communicator. She's, and one of her videos, if I'm recommending her YouTube channel highly because it's all good stuff, but one of her videos is kind of confessional, and it talks about how she was essentially thwarted from a normal academic career, not because she isn't smart enough or doesn't have good ideas, maybe because she's a woman, maybe because she's outspoken, maybe because she just didn't fit into the department she was trying to be a part of. So she's made this sort of parallel existence as commentator on physics and astrophysics on YouTube, and it's high-level content. It's not intensely mathematical. And I think one of her most provocative and best arguments is that physics is going down the wrong path with string theory as a fundamental theory of everything, or quantum gravity, another version of that. She thinks that many of these research programs are doomed to fail, or not well conceived, or that they're just not the right approach to go for. She's also very aware and has commented on the cosmology crisis, and how the fact that it no longer should be an article of faith that the Big Bang has to be accepted as is and may not need major modification. So she's an iconoclast. She's a maverick. She does take sometimes contrarian positions on some subjects, but the ones I've seen, she's always got good points to make, and even if she's wrong in an interesting way.
Excellent. Thank you very much. The next question is from one of our participants who sent an email. Can you explain a modified gravity theory and why it might eliminate the need for dark matter and possibly dark energy, especially if simplicity or elegance is preferred in theories?
So the dark matter problem, because we haven't identified dark matter, but we think something dark that exerts gravity exists and dominates the gravity of normal matter. The dark matter problem is not being resolved very well because we don't know what dark matter is. And because of this, and because this has been going on for decades, there's been a fair amount of traction on altering gravity theory mildly, such that you don't need dark matter at all. It turns out if you change the exponent of an inverse square law by only a few percent, not very much, second decimal place in the exponent, you could do away with the need for dark matter. And so this very simple idea has led to what are called modified Newtonian dynamics theories, MOND. So that's the acronym that's used. Stacy McGaugh, former colleague of mine, we collaborated on papers back in the day, is a big protagonist of this, but it has other supporters too. So this does away with the need for dark matter, but it pays a big price. Because if you alter Newtonian gravity, you alter some of the fundamental symmetry and elegance of the theory, making it more complicated, making it a little more artificial, perhaps making it unnatural, as a physicist would say. And it's not clear that that's a good trade-off. It's also not clear if you need MOND, or if MOND actually successfully observes all the observations about dark matter. It was designed and has done a good job explaining the way galaxies rotate, the rotation curves that were the original measurement of dark matter in the 70s and 80s, but it's not clear it does so well at explaining the dark matter we see by gravitational lensing in the intergalactic medium or in large scales in the universe. So at the moment I would say MOND is a fringe theory. That's not to say that it's not well conceived or wrong. It's just not clear that it's necessary at this point.
Excellent, thank you. And that kind of goes back to Sabine Hassen Felder also, because she's very critical of people who dive off onto mathematical, flights of fancy without experiments and without backing things up with experiments. So you got to be careful of that too. The next question is from Young Astronomical Research Center, who asks, what would you say to a science doubter who says that everything we observe filters through our brains and therefore is not accurate?
Well, it's true that we digest astronomical information by observing it or seeing it and digesting it through our brains. However, the data itself is independent of our brains. I mean, we record data from the universe in all manner of ways. We make images with CCDs. We detect radio waves and X-rays and other ways. Across the electromagnetic spectrum, we collect data. And while we sometimes have to visualize it or convert it into other forms to be able to digest it with our senses and then our brain, that data clearly exists. So I think it would be a very big stretch and a bizarre hypothesis to suggest that these things are figments of our imagination or our brains.
Excuse me. The next question is from Tarek who asks, is there a solid proof supporting the Big Bang theory, or is it possible that the universe is infinite, where there is no starting or ending to it?
I think the Big Bang has its issues at the moment, but the foundational idea that the universe started in a hot, dense state is very hard to refute. The evidence for that is pretty overwhelming. So I think the Big Bang is secure in that regard, as to talking about a universe that was originally much smaller, much hotter, much denser, and now we live in an aftermath where it's become enormous, where the space curvature is very small, if measurable at all, and the density of matter is very low, and the expansion is driven by dark energy to accelerate over time. So this is a big theory, and it doesn't predict dark energy or dark matter. It's just an expansion history. It's just a description physically of what happens in a universe with matter and radiation in it that goes from a very hot, dense initial starting state and becomes bigger. And in that regard, it's a very successful theory.
The next question is from Craig, who asks, did the DART mission work? And can you talk about, does that mean that we are safe from anything that might be detected?
The DART mission is a NASA mission. It's a double asteroid redirect something. I'm not sure of the acronym, all the letters in it. But it was successful. It was a proof of concept. It was NASA approaching a double asteroid and making an impact of the spacecraft on one of them, and then trying to see how that impact affected the orbit of the binary asteroid. And they detected a change in the orbit. That was what they would have expected given the mass of the spacecraft, which is very much smaller, of course, than the mass of one of the asteroids. So it's a pretty small differential effect. But it showed that you can have impact in space, or you can alter the orbit and therefore also, for a single object, the trajectory of something that's asteroid-sized in space. So in a sense, yes, that was a proof of concept of how we would have to operate if we found an asteroid that was headed towards the Earth to create a catastrophe.
The next question is related and from an email. How long do you think it will be before we try to capture an asteroid and put it into orbit around Earth?
Well, this is a premise of space mining, the idea that you judiciously select a near-Earth asteroid half a kilometer across that has large amounts of heavy metals, precious metals, and rare earths. You can determine that spectroscopically before you go there. And deviate its orbit enough to bring it into a very elongated captured Earth-Moon orbit. Not too much energy is required to do that, so the technology to judiciously select a near-Earth asteroid that does come quite close to the Earth and then alter its trajectory to be captured by the Earth-Moon system, that is fairly secure science. It's rocket science, of course, but it's stuff that NASA engineers do all the time. The step beyond that of actually getting the minerals and materials off the asteroid and down to Earth without spending so much money that it's not cost effective, that is very unclear.
The next question is from Terrence, who has some questions about the moon. And I guess we'll start with the sort of ending one that has the most information here. Is the moon hollow? I read on the internet that NASA said that it rang like a bell when they left the moon. So I mean, perhaps there was some kind of seismic effect, and they're interpreting that as because the moon is hollow. Can you talk a little bit about that?
Right. I think the phrase "ringing like a bell" probably has misled some people. The moon is not hollow. The moon is an object that has a very small core, and it doesn't, because it has no magnetic field, and it formed as an impact off the Earth, so it didn't form in the conventional way. So it has a higher density core, but not a sort of metallic liquid core as the way the Earth does. But we can use magnetometer and gravitometer measurements located on the moon, left behind by the Apollo astronauts, or from orbiting satellites, to measure the density of the moon below the surface through its entirety. And so we mapped the density of the moon, and we know it's not hollow. It does ring like a bell, however, because most of the rock is granitic volcanic rock. kind of rigid rock, and so it transmits seismic signals. And so you can sort of tap on the moon, hard tap on the moon, and see seismic signals transmit through it. And that's been done.
Excellent. The next question is from one of our live participants, Young Astronomical Research Center. Again, do you think that the SpaceX Starship is useful, even though it takes 16 flights, 15 refueling ones, to put one on the moon, and countless more to get to Mars and beyond?
I think it's a very important spacecraft rocket, because it's already gone through, I think, 5 test flights, and each time they've improved what happened. The first one was an almost complete failure, except for the early stages of the rocket propulsion. The most recent one, where they captured with these tweezers on a launch tower in Texas, was quite spectacular. So that's reusability of the Starship, which keeps it cheap. It is indeed true that to get to do a fully fledged lunar mission will require a dozen or more Starship flights, but that's okay. Elon Musk is gearing up to scale up this activity, and so having had 5 Starship test flights in less than a year, I think he can increase the pace and the cadence of flights substantially. And so it's not at all out of the realm of possibility that within a few years, as part of the Artemis program, SpaceX can support going back to the moon. And then his eventual goal, as we know, is to go to Mars with the same rocket and the same technology.
The next question is from Zuhair M, who asks, do you think that studying black holes will help us reconcile the theory of relativity and quantum theory?
It's possible. Black holes are the test bed for that kind of a unification, because they are objects formed in intense gravity, and so they're routinely used, black hole properties are routinely used to test general relativity. And we also know that there are particle effects near the event horizon. Some are just theoretical, and a couple have been indirectly observed, which implicate quantum mechanics or quantum physics. So because black holes put us in the regime where both quantum physics and gravity physics are important, they could be the place where progress is made on unifying these theories.
The next question is from Short Educational Videos, who asks, what are the minimum educational qualifications for an astronomer?
It sort of depends on where you work. I mean, we have telescope operators, for example, here in Arizona and elsewhere that I've visited, and they may have an engineering background. There are telescope operators that don't have any astronomy background at all. There are others that have an astronomy bachelor's or physics bachelor's, and that's all, no advanced degree in astronomy, because it's not necessarily required for some of the technical jobs in the field. So that's a broader way of putting it, that the sort of gold standard of a PhD in astronomy to be able to do research is just one way you can be employed as an astronomer. And here in Arizona, we employ lots of people at observatories doing astronomical work and sometimes research that are not formally trained with an advanced degree in the subject.
The next question is from one of our live participants. Dinosaur Spaceship asks, aside from Q&As like this, what are some good ways for non-experts to stay up to date on the latest astronomical research? I minored in astronomy at university, and since leaving, I found it hard to keep up with the field.
Well, if you really want to keep your finger on the complete pulse and have a fire hose of information, you want to go to the archive. So the archive is the preprint server out of Los Alamos that's now was originally used by astrophysics and high energy physics and computer science. Now it's used by biology. BioArchive is a very major repository. So it's a way scientists are now putting up their work before publication, so that's why you're getting it as it happens. The archive servers allow you to do keyword filtering and set up search lists and watch lists, and that's the best way to stay current on a particular topic. So if you're interested in supermassive black holes or massive black holes, you can have those as keywords, and you'll get prompted for how many papers are appearing on that subject. But a warning, it's a fire hose. There are thousands of papers a month written, and tens of thousands a year. And even in a niche field like black holes or exoplanets, which is not really a niche field, it's kind of a big field, you're going to be inundated with papers to read. And they're technical papers, of course. These are the research papers. And they typically exist on the archive as PDFs that you can download or just read there.
Next question is from one of our live participants. Do you think that the universe is simulated, and would there be a way that we could tell?
I don't happen to think it's simulated, but I don't have proof. I mean, that's one of the fascinating things, the simulation hypothesis, as it's called, is that it's very hard to refute, because the premise is that an advanced civilization would make a simulated experience that would be factually correct, that would be very hard to tell from the original. So if we were in a virtual situation that so faithfully mimicked reality that it was indistinguishable, then we might as well be living in a simulation. I don't actually believe that because I think people have underestimated the sort of computational power and skills required to create a huge simulation like that. But it's hard to rule out entirely, which makes it a provocative hypothesis. It comes from the field of philosophy.
The next question from Patti is about supernova. What is the mechanism by which an implosion of a dying star becomes an explosion?
So when these dying star collapses, where the last fusion has happened, typically creating iron the most stable element, there is no energy extracted if you try and fuse beyond iron, so it's not energetically favored. And that means iron is the last stage, the end of the road. And so when the star stops having fusion reactions, there's no pressure support, and the enormous mass of the star, because these supernovae are stars that are about 10 times the mass of the sun when they start, that material is going to free fall in at approaching the speed of light when it gets to the center of the star, and creating an incredible pileup of mass and incredible high density, and essentially creating a rebound. So it's almost inevitable physics that when so much mass collapses so much to such a high dense state, that there's going to be a pushback, if you like, a sort of rebound or a recoil phase. And that is the supernova explosion, which is spectacular in its own right.
The next question is from Toast and Loaf, who asks, dark matter seems like magic. If dark matter has mass, can it be made into stars or collapse into make a black hole?
So dark matter is magic until we figure out what it is. It's a little artificial and arbitrary, and people have their doubts about dark matter. But there's a very strong indirect evidence that it exists on many scales. But dark matter exerts its own gravity, but it doesn't interact with radiation. It's actually the interactions with radiation that facilitate the collapse of objects like stars and galaxies in the universe, because it's the normal matter and the interaction with radiation that allows energy to leave the collapsing cloud, accelerating its collapse. And so dark matter on its own, just a cloud of dark matter, will indeed concentrate gradually by gravity, but it won't do the dramatic collapse and concentration that leads to stars and galaxies. And so dark matter will always be less clumped and less clustered than normal matter, more diffusely distributed. And that's something we expect. And in that sense, dark matter is not particularly associated with black holes, because a black hole is a collapsed end state of a star based on the normal matter of that star. And although there was dark matter present, it was not very much, and it wouldn't have a mechanism to be collapsed into a high concentration.
The next question is from one of our live participants. Terrence asks, is the singularity inside a black hole made of matter?
We presume it's made of matter, but the singularity is a theoretical concept. It's an infinite state of density, so it's being an infinite state of density means it's not matter at all. It's not normal at all, because that's unphysical. So the simple answer is no, the singularity is not matter, because it's essentially an artifact of the mathematics of the theory. And so It's part of why astronomers feel that the current black hole theory and the current gravity theory are not the final answer.
The next question is from Patty, who asks, are there any non-dwarf planets beyond Neptune?
No, it seems like there are no non-dwarf planets beyond Neptune, because we would know. And that's very far, several billion miles, but our telescopes are really good, and we've been surveying the ecliptic, or the band of sky where the planets all appear, for decades. And anything large in a standard orbit that far out would have been picked up a long time ago, actually. So we're fairly certain there's nothing very large out there.
Excellent. Well, it is 10:58, and I think that we are going to wrap up with one final question, and that one is going to be from one of our live participants who would like to know if it's possible or reasonable to create a generational spacecraft in Earth orbit, and what kind of resources would that take and what kind of timeline?
So the idea of a generational spacecraft is one where a significant number of astronauts occupy the spacecraft for multiple generations to go a very large distance. It's a concept that applies to interstellar travel, because you don't really need that technology to travel within the solar system. To travel outside the solar system, you do, because your speeds are just not going to be dramatic, even driven by solar sails or current technologies. Very hard to imagine going more than a tiny fraction of the speed of light. And so you need a multiple generation spaceship where astronauts either live and die in real time or are put into suspended animation until they approach their target to do any of this interstellar travel. And those technologies are not with us right now. So generational starship or spaceship is a long way off, and would need a new forms of propulsion too. So for that reason, I think it's 50, 60, 70 years off at least. Interesting question to end with, and we've had a good range as usual, from black holes to cosmology to small objects in the solar system. So thanks for your questions, and to Matthew for facilitating. And we do have the next few live sessions lined up. We try to keep a cadence of once every 2 or 3 weeks, but we will have a gap of a month over the Christmas and New Year season because so many people are busy, including us.
Excellent. Yes, thank everyone. Thank you to everyone for joining us. Again, make sure you like this video or like this stream, and subscribe to our channel. Click that bell icon so that you get all of the alerts for our upcoming live sessions. We have them about every 2 weeks, like Chris says. We have the next 4 of them scheduled, so I'll real quickly go over those. So we have one in 2 weeks on Wednesday, November 20th. We have one in 4 weeks on Thursday, December 5th, and then we have our hiatus over the holidays, and then we come back January 7th on Tuesday, January 7th, and then again on Wednesday, January 22nd. So if you didn't get all of those, that's fine. You can join our email list, so scroll all the way to the top of the chat. You can join our Google listserv, and we always send out announcements and reminders about those things. But they're also on our channel, so we've got those live session dates already posted. You can set a reminder for those on the YouTube channel, and it will alert you that when that it's coming up and when it starts. So thank you to everyone for joining us today. We hope that you have a great week, and we will see you again in 2 weeks. Thank you for joining us, and have a great day. Take care, everyone.